technological progress. But whenever any material is developed, that material must be studied whether this material has been developed with its the expected properties or not. And in this direction, materials are characterized after fabrication, sometimes during fabrication for monitoring the production. And also whenever one material is used for developing any device and during the operation of the device or structure, if the material is deteriorating with time or any damage, then that material is also required to be either monitored, replaced if it is needed. So real-time monitoring is also very important. So there are several types of characterizing process. There are several types of non-destructive evaluation process. Even some destructive processes are also there in the laboratories, but non-destructive methods are often uh, very useful and required in many cases. So the techniques which are used for characterizing method, that varies from type to type depending on its physics, depending on its the signals which is applied. So many methods, either non-restrictive or say a non-invasive type of monitoring, have been proposed by several research groups. Uh, Among those non-restrictive testing, there may be few of them as the X-ray based monitoring, ultrasound based monitoring, magnetic methods, eddy current techniques, and impedance based monitoring. The impedance based monitoring technique is comparatively new technique where the materials impedance, that is fully called electrical impedance, is monitored. So we will discuss about the electrical impedance based methods, and then gradually we will move towards the uh, how the nanoparticles can be found as helpful for electrical impedance methods. Okay. So we will be discussing as per the outline. So introduction to the impedance, what is bioelectrical impedance. I will tell the a little bit about the bioelectrical impedance techniques, because the impedance based techniques has found a very good application in biomaterials and biotechnology. So there are a lot of information hidden in the electrical property of material in each field, but in the field of biomedical we have seen the material impedance has the information about not only the health condition but also some disease informations are also hidden, so that can be extracted with proper analysis and we can detect several number of diseases. And after that we will go for that impedance based material characterization technique, that is I have abbreviated as, because it's a very big phrase, so I have abbreviated as IBMC, that is for human physiology and disease. Then the IBMC nanoparticle based IBMC for biology, and then the cell monitoring, and I will go for the civil structure, some composite materials. So I will try to cover several types of materials which can be properly studied or characterized with the help of electrical impedance methods. And if we use the nanoparticles in these techniques, then the procedure will be having some more sensitivity. So for enhancing the sensitivity, nanoparticles are included in the material. So that will be also discussed in brief. So we will start with some electrical property of the component, electrical component, like electrical source, because there may be some participants from different field where the electrical impedance may not be very much say well-known parameter, or they might have not worked more on this electrical impedance. So I just making some fundamentals or the basics so that they can feel good to go towards the electrical impedance based techniques. So if it is known to all the participants, then I will quickly go through that. So I hope no one will be feeling bored, or they will not feel that the time is lost for this type of basic discussions. I will quickly go through this basic discussion, and I will go to the electrical impedance based techniques. So electrical source is a device or the component in electrical engineering which has the capability of delivering some power. So it will give power, and a basic example is battery. Symbol of battery is given here, and if any source is connected with a closed circuit through a load or any conductor, then current will flow due to this potential difference of this source. And electrical load is another component which has the property of absorbing electrical power. That means it will take the electrical power or receive the electrical power from the source. So load will take the electrical power. Example of loads will be resistor, capacitor, inductor, or many more, or combination of them. And the signal, whenever some electrical energy is to be transferred from one point to the other point of a conductor, there might be potential difference. So if the circuit is closed by a conductor, then that potential difference of the voltage will send some electrical power or energy to the load in form of the flow of charged particles, either electron, or it can be conceptualized with some positive particles like holes. And the flow of the electrons are considered as the electrical current. The direction of the electrical current in conventionally is taken in opposite to the flow of electron because electron's charge is negative. So the direction of current is considered as the direction of the flow of the positive particle, that is just opposite to the electron flow. So whenever there will be some electron flow or charge flow in a conductor or in any closed circuit as shown by this material, so we have seen that current flowing through this load is nothing but the flow of charged particle in a particular direction depending on the polarity of the battery connection or the source connection. And then this type of flow can be mapped or can be drawn in a form of time varying signal, whatever shown in here. So whenever the source will be DC source, if the DC is taken as the ideal source, then the rate of flow will be constant over time for a particular duration whenever it will be having the capability of delivering charge. And sometimes this DC also can be fluctuating in nature. So why it is called DC? Because it is flowing in a particular direction. So that's why it is called direct current, and its polarity is not changing. Polarity will only change whenever the signal will cross the time axis and it will come down. That means its polarity will remain positive whenever it is at the top side or upper side of the t axis or time axis. Whenever it is touching that, that means it is becoming zero, but whenever it is coming down, it is getting negative. So amplitude is changing means its polarity is also changing. Here amplitude is only changing, but polarity is not changing because it's not crossing down to the t axis. So that's why it is also direct current, but direct current with some amount of ripple. That's why it is called ripple DC, or this type of DC is called fluctuation DC or fluctuating DC, and this DC is called pure DC. Now in case of alternating signal means it will be changing its amplitude as polarity. So the amplitude and polarity can change with a periodic manner. So that's why some signals are periodic in nature, some may be non-periodic. That means it will not be repeated with a particular rhythm. So as shown in by this blue curve, so that will be called as non-periodic signal, but the red and the pink curves are periodic in nature, and the form of this signal is sinusoidal nature. So as we have discussed that some charged particles are required to be moved in a particular direction for DC current. So here we can see by this animation that electrons are flowing in a particular direction and the current is flowing through this load, which is lamp here, and that's why it is called DC current. And as it is flowing in a particular direction, as the polarity is not changing, so it will be always in the one direction, either in positive y-axis or negative y-axis, but it will not change with time. But in case of alternating current or alternating potential, say for alternating current, the direction of the charged particle will change with a particular time duration, and the repetition rate is called frequency, and that is decided or defined by the property of the generator running in the power plant for generating the electricity. So here we can see that the polarity is being changed with time, as well as the amplitude of the signal is also varying with time. So if the sinusoidal signal is taken, we can see that the amplitude is starting from 0 to maximum value, and again it is going down to 0, and then it is going into the negative axis. So this first generation, time of generation to the time when it becoming 0, that cycle is called half cycle, and this is another half cycle. So this is positive half cycle and this is negative half cycle. So including one positive half cycle and one negative half cycle, one complete cycle is formed. So this is about the nature and behavior of any sinusoidal alternating signal as it is shown here. So AC current. So now whenever any alternating potential will be applied across any load like resistor, capacitor or inductor, then what will happen? Current will be produced because path is closed. Depending on the nature and behavior of the material connected, say material is either capacitive or inductive or resistive, the current and voltage will be in a time axis. Means there will be sometimes there will be some phase displacement and sometimes there will be no phase displacement. For resistance there will be no phase displacement. The amplitude may vary depending on the resistance of the circuit, but the instantaneous value or the rate of change of the magnitude will be same. Means they will start at the same time and they will reach maximum value at the same time. Again they will go to the 0 at the same time. So there will be no phase displacement, means there will be no time displacements in their generation. But in case of other parameters like inductor or capacitors, we have seen that these signals are not in phase, means they are not generated in a particular time. In the same time they are not generated. So for the register they will be in the same direction. In the phasor diagram also we will see that they will be lying in the same direction and there will be no phase displacement whatever is observed in case of inductor and capacitor. For pure inductor and capacitor there will be 90-degree phase displacement. That's why you have written this or drawn these vectors with 90-degree displacement. And the difference between the inductor and capacitor is that the current will be lagging behind the voltage in case of inductor, and in case of capacitor the current will be leading over the voltage. So the purple arrow is representing the current here and blue arrow representing the voltage here in this vector diagram or in this time diagram. So but what will happen when there will be several materials connected together? Means if some resistive material and inductive material or resistive and capacitive or all of them are combined either in series or in parallel, so there will be combined effect. So if we study the behavior of them, their combination, the phase angle or the impedance will be found as per the combined effect. So there will be several formula and there will be electrical theories or the circuit theorem by which we can calculate the response of the circuit. So here we have seen one series circuit where resistors, inductor and capacitors are connected in series, and it is very easy to calculate the amount of the total impedance after calculating the inductive reactance and capacitive reactance. Inductive reactance is the property which tends to oppose the current passing through it, and it is also dependent on the material property, that is inductance, as well as the frequency of the signal applied. For the capacitance also, the capacitive reactance, which is also produced as the oppositional property to the alternating current tending to flow through this element. So it is also dependent on the inherent property of the material, which is capacitance, and as well as the frequency of the material. But resistance is not creating any reactance. It is only creating the resistance. So the impedance of this material or the inductor and the impedance of this capacitive element or capacitor will be capacitive reactance, and impedance of this material or this resistance will be resistance itself, and the total impedance will be combined or calculated by this formula. So XL stands for inductive reactance and XC stands for capacitive reactance. Depending on the material, it will be found that either capacitive property or inductive property is dominating, and depending on the material, either capacitive or inductance is dominating in nature, we will get the ultimate inductance, ultimate impedance, and the phase angle. So if we apply the alternating current to across the resistor, summary is that we will get the resistance itself, and that will be considered as the equivalent impedance of the circuit. But if we apply some alternating current to a resistor, capacitor, and inductance, then we will find the capacitive reactance produced by this material capacitance will be 1 by omega c, and the inductive reactance produced by the inductor, it will be omega L, where omega is the 2 pi f, and this 2 pi f is dependent on the frequency, and 2 and pi are constant, as we know. So automatically the capacitive reactance and the inductive reactance will be dependent on not only the material property but also frequency. Material property is either capacitance or inductance. So if the capacitive reactance is more, then this sign will become negative, but if inductive reactance is more, then this will remain positive. So depending on that, we will get some phase angle, either leading phase angle or lagging phase angle, which can be calculated by this formula. So this was the basics of phase and the impedance, how the material impedance will be there for standard elements. But whenever we will study some material having some resistive properties, how the material impedance is found. So whenever some material is there, depending on the material composition, material structure, and material arrangement, the material impedance will be found. And it is very difficult to find the or calculate mathematically the impedance of a particular 3D material or 3D sample of the material. So it is much easier if we want to measure the impedance with some technique called impedance measurement technique. So we often do that. If one piece of brick or one piece of concrete is found as a sample, and if we want to measure the impedance, then we will not find anything inside that. If we break and if we see with microscope, we will never see any resistance or capacitance or inductance with that type of symbols or that type of representation. So we will find only the particles by which this material is made. But for any material, whenever the material is having a three-dimensional structure, so definitely there will be some particles which are arranged in 3D arrangement, and due to the arrangement, due to the property of the microscopic material, or due to the property of its unit material by which it is developed, its impedance will be defined, and that impedance can be monitored with the help of impedance measurement technique. So after measuring the impedance, we will see several information can be extracted to characterize the material. So we'll go gradually towards that direction. So here I have again summarized that depending on the property of the L and C, we will find the impedance and the phase angle. So now suppose we have one piece of material as a sample where we have to measure some electrical property. So electrical property can be found either applying DC current or AC current. If we apply the DC current, then we will be able to measure the resistance. And if we apply the AC current, then we will get the entire characteristics of the material, because we are not sure whether the material will be purely resistive or not. If there are some capacitive material or inductive material, and if we apply the DC current, then its entire information will not be obtained, because in case of DC, the capacitance works as the open circuit and inductance works in the series circuit. So there will be some wrong identification or wrong information which will be probed by this DC technique. So only resistive property will be measured by this technique. So we generally apply the alternating current, and we have understood already what is the alternating current and how it flows and how the impedance is created by the material if the material has a resistive element, capacitive element, and inductive element. So the technique is very simple. Just remembering the Ohm's law, we can calculate the impedance. For the DC circuit, if we apply any DC current, and if we know the dimension of the material, say length, width, and height, then we can apply some current and we can measure the voltage, because whenever current is flowing through any material, voltage will be developed as per its electrical property. So that electrical property is nothing but the constant of the proportionality, which is represented by Ohm's law. That is the current flowing through a material is proportional to the applied potential. So this proportionality constant is resistance, and this voltage can be probed by the known value of the current. So if we measure the voltage across this, Suppose we have electrode here and electrode here, and if we are sending some current and we will see some voltage has developed. Now whenever we will get some voltage value across this surface and that surface, then we will be having some proportionally constant as R, and this is nothing but the resistance for the DC measurement technique. And now we know that if we know the dimension of the material, we will be able to calculate the conductivity also if the resistance is known. So resistance is known from this equation, and the resistivity will be known from this equation if L and A is known. Now A is nothing but the area of the cross section through which the current is passing. So definitely we will be able to get the value of resistivity. So the same thing is conducted in case of alternating measurement, but the gain is that means gain means here is not the amplification gain. The gain means the extra things what we are getting or extra information what we are obtaining here. That is the information about the entire electrical property, not only the resistance, because we are sending some alternating current. So definitely it will be interacting with the capacitive element and inductive element. If anything is there, then we will get a certain amount of impedance. So we are not calculating the impedance with the help of any series parallel combination of resistor capacitor inside it. We don't know anything. It may be a black box. There may be two electrodes pasted on these two sides, and we are sending some current and measuring the voltage, and after dividing that voltage by known current, we can get the impedance. So this is the techniques. So here I have just given one animation for giving the concept of the phase, because impedance will have some leading phase and lagging phase. So it is nothing but the time at which any wave is generated. So there may be some time difference, just like of the any human being. Somebody is born in some earlier time, and then after some time somebody else has got the birth. So definitely they will be always lagging with some months or days or years. So even for the siblings also it happens same time. So similar thing. So they will be having some time displacement in their birth time. So same thing for runners also. If the runners are running in a track, say some runners like the green runner may be in leading position, they may be ahead. They started at the earlier time, and some runner will have some say lagging behind some other leading runner position. So now if this green runner is considered as current, and if the red blue runner is considered as the voltage, so we will tell that the current is leading over the voltage, and in same property or same phenomena can be represented with some lagging term, that the red blue runner is lagging behind the green runner. So if the circuit is capacitive here, we will see that current is leading over the voltage, and if the circuit is inductive, the voltage is leading over the current. So this is the concept of inductive circuit and the capacitive circuit, where current and voltage has some phase angle. Okay, so we have already discussed about that. So now if we have some unknown object, and if that object is to be measured or to be is required to be studied, we will inject some alternating signal which is represented by the red sinusoidal curve. And now we can apply the voltage and measure the current, and we can apply the current, we can measure the voltage. Both are possible. So when the current is applied and voltage is measured, that type of technique is called applied current impedance measurement techniques. And if voltage is applied and current is measured, that is called applied potential impedance measurement technique. So either applied current or applied potential, both can be done. Here we have taken as applied current, which is most popular and majorly used that type of technique. So applied current means we will generate some sinusoidal current with constant magnitude. So we should note that, we must note that current amplitude must be constant, and then we will get some voltage. So whenever the current will be applied on an object, some voltage will be measured, and that voltage will be obtained as sinusoidal wave and with the same frequency. So what do we have to do? We have to have some current source, and that current source will have two terminals, and those two terminals will be connected to the object. And we will have, or we must have, one voltage measurement device like voltmeter multimeter, or any other data acquisition system by which we will be able to measure the alternating potential or alternating voltage developed across this material. So an impedance measurement circuit contains current source, signal conditioner, and voltage measurement system. If the signal of the voltage has some say noise, then the signal should be passing through the filter, and if the voltage available here is very less, which is not suitable for measuring with a particular device, then we must incorporate some amplifier. So that type of circuits will consist of say amplifier and filters. The signal conditioner is called. So that type of signal conditioner sometimes required, but basically current injector or current source and voltage measurement device as shown by this picture. So Z is calculated by Ohm's law, and it is found as, so if the current is applied, the current is taken as the reference, and that current is taken as Im sin omega t form, which is the standard form of representing a sinusoidal wave. And now whenever it will pass through the material and whenever it will develop some potential, depending on the material property, that is whether material has some resistive component or capacitive component or inductive component, or the combination of them, accordingly the phase angle will be developed, and that phase angle will be either positive or negative depending on the material dominating property, either capacitive or inductive. So this type of voltage will be developed, and that voltage will be found again in the form of Vm sin omega t plus minus theta, and we will get the Z as the impedance amplitude and with the phase angle plus minus theta. And that material can be obtained or that material testing can be done either with 2 electrode method or 3 electrode methods. As is mentioned as 2 probe method or 2 electrode method, it suggests that it will be measuring impedance with only 2 electrodes as shown by these yellow boxes. So 2 electrodes means the current injection will be conducted through these 2 electrodes, as well as the voltage also will be measured across these 2 electrodes. So this type of method will be suffering from contact impedance problem, because the current flowing through these electrodes are also, the contact impedance is also coming in the circuit of voltage measurement. So voltage, the device voltage will be also added with the contact impedance drop. So in case of the 4 electrode method, that problem, that is contact impedance problem, is avoided. And here you can see that, as the name suggests, that 4 probe method or 4 electrode method, there will be 4 electrodes. Here 2 electrodes are used for the current injection, and the current injection electrode should be taken as the outer electrodes, that is, it will be placed at the extreme positions, at least away from the voltage measurement electrodes represented by the blue electrodes. So voltage electrodes are placed at the inner electrodes as the inner electrodes, and the current injection electrodes are placed as the outer electrodes. Whenever the current source will be working or sending the current, so current will pass through this material and we will be measuring the voltage. So in this case, 2 things is very much important. First of all, the current electrodes should be placed outside of the voltage electrode, because current will be passing through this point to that point. That means there will be voltage developed across this material. But if there are some other material projected till this point, that material will not have any current conduction. So if you put some material, will not be get the proper voltage. But as the current path is covered from this point to that point, that is red 1 electrode to red 2 electrode, we will be able to measure the potential measurement nicely here. But if you just think, if the current has, if current would have been injected here in this portion, and we are measuring the potential here, that means from this portion to that portion there will be no current injection or no current flow. So there will be some wrong measurement or wrong value will be coming. We will not be able to get the actual potential. So that's why current electrodes are put at the outer side and voltage electrodes are put at the inner side. So that is the procedure, and the reason behind it has just mentioned as we have noted here. So we have to consider this type of rules, and we have to follow, so that we cannot be say diverted in the measurement errors. So, and another thing is that we have to have some particular space between the current electrode and voltage electrode. Otherwise, if these electrodes are touching each other, then it will be converted to the 2 electrode method. So impedance-based health monitoring, I will come to that point, how the electrical impedance are helping us for health monitoring for the material. So our human body is a complex structure, biological structure, where some biochemical and biological phenomena are happening and taking place day by day, periodically and regularly throughout the life to keep our body healthy and alive. So several cells are combined to develop some tissues, several tissues are combined to develop some organs and some body parts, and all the organs and body parts are developing our entire body. So there will be several systems which are responsible for particular work, like muscular system, skeletal system, circulatory system, nervous system, and lymphatic systems. And the systems are also developed with several organs. So that organs are performing their work, assigned work regularly and repetitively throughout the life to keep our body alive and healthy, like say heart, lungs, and the kidney, ear, eyes, and so many organs are there which are extremely important and for keeping our body healthy and alive. So but at the ancient age, at ancient time, when our medical science was not so developed, the doctors were trying to get some superficial information through either visual observation, touch sensing, and hearing to detect some health problem or if a disease is there. So during that time, no medical experimentation was possible to be conducted, or any instrument was not available. So very small instrument like say any pipe or anything else for getting clear signal or clear sound. So that type of signals were not very clear and also not very accurate also. So their diagnosis was suffering from some accuracy problem, as well as they are not sufficient to detect a particular health problem. So many lives were not possible to saved during that time, unfortunately. So gradually our science and technology has developed, and we got several instruments, and the several disciplines are combined to develop the improved material with say more accuracy, like biology, medicine, and engineering are combined to develop the biomedical engineering field, where we found several technology can be developed. With the help of technology, the device can be developed, and with the help of the devices or instruments, several experimentation can be conducted to save our life, to study our health condition. So the researchers, scientists, and engineers from this biomedical engineering field are developing their technology. They are studying the theories and they are developing their own theories. After that, with the help of the utilization of the technology and theories, we are able to develop some products in industries. And whenever the products are developed or instruments are developed, those are used by doctors, medical practitioners, and clinicians to health studies. So many devices are used for tissue diagnosis, say biological material analysis, and our disease analysis. And disease are also possible to be detected by analyzing our body fluid, by analyzing our tissue, by analyzing our cells, and after monitoring several vital signals also. Because all these cells, tissues, and vital signals are influenced by the health condition, and if health condition is proper or healthy, then there will be one kind of signals coming out from those materials, and if those are suffering from disease or abnormal health conditions, then also the signals will be influenced. So after measuring the body signals and vital signals like temperature, blood pressure, ECG, the materials parameter like material say structure, material development rate, all these signals can be obtained by biomedical instrumentation and the measurement techniques. And after analyzing that data with the standard one or normal data, we can uh, consider, or we can decide whether the health is in normal condition or abnormal condition. So the experimentation or the procedure of judgment may be invasive, minimally invasive, or non-invasive, and sometimes it will be non-contact also. It may be wireless. The signal type may be temperature, blood pressure, oxygen saturation, and all. Some techniques are also imaging devices. So that type of imaging which is done by the X-ray, that type of imaging is very useful for medical diagnosis, where the tissue contrast will be obtained as the image representation. So signal measurement can be found by blood pressure, electrocardiography, electroencephalography and all, and where the electrocardiography can be found as a portable machine and putting some electrodes here. So, and for the EEG or electroencephalography, the brain potentials can be obtained as a signal, and this signal will be having several kind of information related to the brain health and the health condition of the nervous system. And the vital signs which are very important for diagnosing the critical ill patients either in ICU or in emergency, that should be monitored for a long time. That type of monitoring is found in ambulance also, that is called ambulatory monitoring. So that type of signals are weight, temperature, blood pressure, heart rate, ECG and SpO2, that is the oxygen saturation in the blood. So those type of signals are continuously monitored to diagnose our tissue condition, health condition. So many diagnostic techniques are found with the help of some measurement devices. Either the electrical signal is measured from the heart, or the pressure signal is measured from the blood flow, or the tissue contrast is obtained from the X-ray planar radiography. But in some cases, the computed tomography or imaging technique is preferred, because in these three cases, as for example, all the signals are coming as the graph, time varying signal. We are not getting any image of the chest or image of the heart or image of the transthoracic region. Here also we are not getting the image of the brain. Here also we are not getting the image of the cross section of the hand. So here all the signals are coming either as a value or as a time varying amplitude, which can be plotted in a graph. But here in case of tomography, computed tomography, some signals are applied throughout the 360-degree angle. So the applied source will rotate across the body, and it will collect the body information at a particular angle, which is called projection angle. So it can be conducted with X-ray, magnetic field like MRI, or any other gamma rays in a positron emission tomography or single photon emission computed tomography, or it can be also obtained as ultrasound imaging or fluoroscopy or endoscopy. Endoscopy is one kind of direct imaging technique where the tomography is not applied. Here only one pipe is inserted in the mouth with the help of some the tip based camera, means micro camera, which will be placed in the tip of the pipe, and that camera will be controlled from a computer, and that camera will be able to take the picture of the interiors, body interiors, either food pipe or stomach, so that we can get some information which is helpful for diagnosis. So these are the say schematic of several medical diagnostic technique which will help us to diagnose some disease or health condition. So these techniques are not all the impedance based techniques. So whenever these techniques were found, definitely like any other techniques, all the methods will have its advantages and disadvantages. But as human beings are curious, so they tried to study the interaction of electricity with the body tissue. Luigi Galvani was experimenting with the frog's legs, and he found some interaction with the electricity and electrical conductor with the muscle tissue. And after that, William Einthoven were able to get the electrical potential generated by the heart by the great invention in electrocardiograph. So this is the first electrocardiograph he has developed, and with the help of 3 electrodes, where these electrodes are nothing but 3 tanks filled with saline solution. So any material which are conducting or good conductor in behavior, that type of conductor can be connected to a body to work as an electrode. So he developed his own electrode as the saline solution poured in a particular tank. So he dipped his 2 legs, 2 hands, right and left, and the left leg, and 3 electrodes based ECG was performed. And after that, people realize, like any other material, biological tissue also will have its own impedance. So how the biological tissue will have its own impedance? So whether the biological tissue or the cell will have capacitance or inductance, what type of property will be there, or the resistance will be also there, or combination of those material will be there. So if we take any isolated tissue section, Then if we put that tissue in a microscope, we will see that several cells are arranged in three-dimensional nature so that it can develop a 3D structure. It is true for the animal as well as it is true for the plants. So whenever we will see or we will cut any tissue section and if we put in the microscope, under the microscope, we will see the three-dimensional array of cells are there to develop the tissue structure. And depending on the organs also, the tissue structures, tissue property will be different. So heart tissue is different from the muscle tissue, other muscle tissue, and the muscle of any eye will be different from the muscle of kidney. So that type of material is that type of information should be noted. And if we take one say tissue material and if we put two electrodes across it, then as we have studied the impedance measurement techniques, we can conduct the same technique and we can get the impedance for this tissue. So, but how the impedance of the tissue is formed? Definitely there should be some material which are either producing some inductive property or capacity property. What is there actually? So if we take an isolated cell surrounded by the cell fluid or the body fluid, then we see that the cell is surrounded by one cell membrane, and the cell membrane structure is developed with protein lipid protein bilayer, where the impedance will be where the capacitance will be produced from the cell structure. So the protein is the hydrophilic material which is a water loving, so it will contain a lot of water, and the other protein layer also will same, but the internal the lipid layer, that is oily in nature, so that is a fat and that is hydrophobic, so it is water hating material, so it will not have any water inside it. So definitely the material which has more water and which has less water, so that more water will be conducting, and then the other conducting material, and both the conducting materials sandwiching one insulating material, so there will be some capacity property from the cell membrane. So due to this capacitance, abbreviated as cell membrane capacitance, we will get some capacitive effect from each cell, and that capacitance property will be combined with some other resistive properties as it is mentioned by this slide. So if we have one isolated cell and cell is developed with the cell membrane and the intercellular fluid, and if we assume that there are two electrodes connected across this material, then current will have two possible paths. One is through the ionic medium or less resistive material, that is extracellular fluid, and the other material which will be through the cell. Now, if you enlarge the picture here, we will see that capacitance will be created by the cell membrane, and also whenever current will pass through this material, the current has to pass through the cytoplasm or the intercellular fluid, which is created by the saline solution. When salt solution, many kind of salt will be there, and also organelles will be there, cell organelles. So if we assume that the material property is created by this RICF, that is the intercellular resistance, then the current path is similar here, so they will be connected in series. And in case of the extracellular fluid, when the current has the possibility to go through that, so it will face some resistance produced by the extracellular fluid, which is also ionic medium. So you will get two parallel paths, and which will give us the entire equivalent circuit of the isolated cell. So we will get that type of standard cell model, though there are some other cell models are also proposed by several research groups, but this model has been adopted in major number. So that is one of the example of one equivalent circuit of a isolated cell. So whenever we will go for the plant cell, we will see that the cell will have some cell membrane as well as some cell wall. So due to the cell wall, the circuit will be modified, and there will be some other parallel path which will be giving some cell wall resistance, and that cell wall resistance will be again combined with the extracellular fluid, because extracellular fluid will be also there surrounding the cell. So we will get this type of model for plant cell. Okay, so if we have a tissue model, so cell equivalent model for the impedance is understood, and whenever there will be several number of cells, if we take a 2D model of this, and if we are assuming that current is flowing or some electrode is applied here and electrode is put here for sending some current for current excitation, alternating current excitation, we will see that at the low frequency 1 by omega c will be having a less value. Now the impedance will not be, inductance will not be there, because due to the Maxwell theory. So for low frequency, which is applied for the biological impedance measurement techniques, so inductive effect of the tissue will be negligible. That's why there will be no inductance. So only capacitive property will be there and resistive property will be there. So now if we are injecting current at a very low frequency, then this omega will be less, and as the denominator is less, definitely the capacitive reactance, that is the impedance provided by the capacitance, that will be high, and that high reactance or high impedance of the cell membrane will not allow current to pass through it. So as the current has the property of conduction through a low resistive medium, so it will be passing through the extracellular fluid and it will bypass that. But whenever the frequency will be increased at the sufficient say value of the frequency, larger value of frequency, the denominator will be less, and due to the reduction in the the denominator will be more at the higher frequency, and with the increase of this value, the impedance will be reduced significantly and it will be suitable for allowing the current passing through it. So at the high frequency, current will pass through the extracellular fluid as well as the cells. So if we inject current and if we tune the frequency as per the current conduction property of any cells and tissues, then we will be able to measure either the impedance of only extracellular fluid or the extracellular fluid as well as the cells. So if we subtract that, we will be able to get one idea about the extracellular fluid impedance as well as the cell impedance. So that type of phenomena can be understood in any computer simulation also. If we model a particular cell and if we inject the current with different varying frequency, we'll see that with the increase of frequency, the current flux lines are almost uniform throughout the domain. But in low frequency, you see that the current flux lines are trying to avoid the cell due to the higher impedance path. So that type of studies can be also modified with the modified cell structure, or single cell structure, or multiple cell structure, and we have seen in several phenomena, several examples that if we increase the frequency, then we will see that current flux lines are uniform, so that the current at that frequency is seeing in one uniform medium where the cell membranes have produced very less impedance. So the impedance of cells will be matching with the impedance of the extracellular fluid, so entire medium will become homogeneous at that frequency. But in real case, it is not homogeneous. Okay, so the impedance measurement instruments are commercially available. That is called impedance analyzer, and that impedance analyzer will have 4 terminals. So 2 outer probes like current probes, and 2 inner probes is called voltage probe. That can be connected nicely with a sample, which will be say either biological or non-biological, any material, and then we will set some value of the frequency, and we will set the value of the current amplitude, and then we will get some impedance value. So, but in case of impedance spectroscopy, so till this point we have measured the impedance, or we understood how to measure the impedance at the 2 electron method or 4 electron method, but that was explained at a particular frequency. But here, in case of electrical spectroscopy, the word spectroscopy has 2 words, that is, one is spectra and another is scopy. So the scopy or the scanning, that is giving the concept of observation. So we are doing some experiment by which we will get some information, and spectra means it's a band. So band of what parameter? Band of the frequency. So within a frequency, we will try to get some information or investigation. And what type of investigation? The investigation which will reveal or which will measure the electrical impedance. So that's why electrical impedance spectroscopy is nothing but measuring the electrical impedance within a particular band or spectra. So what we'll do, the instrument starting frequency will be given and ending frequency will be given, and within that band, say frequency 1 and frequency 2, how many data is required to be collected. So that type of technique is called electrical impedance spectroscopy. So what we'll do, the instrument will inject the current at the frequency 1 and it will measure the voltage, and from there it will collect the Z1 and Z theta 1. After that, it will shift the frequency from 1 to 2. It will measure the Z2 and theta 2. Like that, it will go for Fn, for which it will measure the Zn and theta n. So we can plot that we can tabulate that data, and from the Z1 and theta 1 we will be able to calculate the real part of this impedance, that is R1 and X1 and so on. So we can go for the calculation of real part and imaginary part from the frequency 1 to n. And if we have the dimension known, then you can calculate the other parameters also. And if we plot the real part and the imaginary part in xy, say this will be a y and this will be x. So, and if the real part is plotted across the x-axis and if the imaginary part is plotted across the y-axis, so we will get one plot which is known as Nyquist plot. And that Nyquist plot will be having the information about its electrical impedance of this material under test. If we analyze that curve, that semicircular curve, in most of the cases that is not visible as the semicircular. So during that time we need to fit that curve in a semicircle, because the curve will be semicircular in nature as per the theory, and we will be able to get the equivalent circuit, and that is called equivalent circuit modeling. So what is the summary of the electrical impedance spectroscopy? We inject the current, and Z is calculated by Ohm's law. And if we inject the current and if we change the frequency, that is if we do the EIS, so we will get the impedance spectra, which is known as a Nyquist plot, and utilizing that spectra or analyzing that spectra, we will get the equivalent circuit. And with the help of the equivalent circuit and circuit parameter, we will be able to detect the tissue or tissue health. So this is the key point of electrical impedance spectroscopy applied for the biological field. And in case of any material analysis, like say any analysis for any nanomaterial or any thin film deposition, similar technique is very popular, especially for the photovoltaic cell characterization. Whenever we have to design some photovoltaic cell, we have to do that for getting the higher frequency, higher efficiency, and for the material selection also we have to think several parameters about the cost and the efficiency. So many people are working for developing or fabricating the photovoltaic cell or the similar devices which will have the proper property or expected property. So whenever the material is developed, if the property is obtained or not, that should be understood or tested. So that type of requirement is fulfilled by many type of non-restrictive testing. Among the non-restrictive testing, electrical impedance spectroscopy or electrical impedance methods are found as fast and low-cost technique and portable technique, which can be applied for measuring its electrical impedance to extract the material property information. So whenever the photovoltaic technology will develop some photovoltaic cell, so several parameters are measured with the help of electrical impedance spectroscopy. So photovoltaic cell is taken as an sample, and that 4 electrodes or 2 electrode method based impedance is measured at different frequencies. After that, the impedance spectra is developed, and that spectra is analyzed for getting the equivalent circuit of the photovoltaic cell. And after getting the equivalent circuit of the photovoltaic cell, we will be able to detect whether any junction capacitance or any say resistance created by the junction, that type of properties are obtained as per our design or not. So that type of material testing can be obtained by EIS. So this is the theory about the electrical impedance spectroscopy, how the circular or semicircular curve is coming. In case of biological material, minus sign will come because it is only capacitive in nature. So for the capacitive circuit, there will be R minus Jx. For inductive circuit, there will be R plus Jx. So if we calculate the impedance for a particular frequency, and if we go for the frequency sweeping, we will get that the profile of the impedance spectra will be in semicircular nature by this mathematical representation. And for the basic theories, I will tell that. So if there are some components connected in a series or parallel, either resistance and inductance are there, or resistance capacitance are there, then we will get different kind of spectra. So for the inductance and the resistance, if they are parallel and connected in this equivalent circuit, so if we do the impedance spectroscopy for that, we will get the spectra like this. And if we have some capacitance connected in parallel with some resistance, there will be spectra at the bottom side. So we might have noted there the X was put at the say above the x-axis. So this X is nothing but the imaginary part. So it has been put with minus sign. So for the capacitance, actually it will come at the bottom. For taking it the top side of this axis, this quadrant, I have put the minus sign here. So this will be minus value of the reactants. So that's why it will be coming at the say fourth quadrant of this. And if we have inductance, it will be at the first quadrant. So now if we have any resistance connected in the series with this parallel combination, so the curve will start from a particular point from 0. But here in both the cases, it is starting from the 0. If any series resistance is there, it will be starting at a particular point, which is away from the origin. And this amount of resistance is called the series resistance. And if there are two parallel combinations with say C1 and R1 and C2 and R2, there will be two different and distinguished semicircular arc. And if any series resistance is there connected in series, so there will be certain gap. So these are the theories, and few of the theories can be understood from these graphs. There are plenty of combinations which can be studied by impedance spectroscopy. And after that, if we have an unknown material and we are getting similar well type of curves, then we will be able to get the equivalent model from this theory. Okay, so there are the other theories, and utilizing the methods of the impedance based techniques, we can get several diagnostic tools like bioelectrical impedance analysis, abbreviated BIA, impedance plethysmography IPG, and impedance cardiography ICG, and the impedance spectroscopy as we have already studied. So impedance based analysis, that is bioelectrical impedance analysis, is a 4 electrode technique, 2 electrodes on the hand and 2 electrodes on the leg, and it will be able to collect the impedance values of the tissue and the body parts depending on the position of the electrodes. So the impedance of this portion starting from this leg, right leg to right hand, it will be giving the impedance, and after applying some formula or mathematical theorem, we can get the tissue property of the some body under test, means subject under test. So it is possible to get or calculate the total body water, total body mass, fat free mass, or the total body fat. So that type of information is very, very important, and commercial devices are also available for this type of impedance analysis, which is very, very helpful for detecting several type of disease, even including cancer. So, and in case of impedance plethysmography is nothing but the procedure of measuring a particular volume of a liquid or fluid. Here in a body part, like the arm, if we put the electrodes, ring electrodes, or say ring electrodes is better, or even for the surface electrodes like say ECG electrodes are also possible to apply whatever is done here. So this type of technique will allow us to measure the blood flow and the calculation of the blood volume which is coming inside this limb and which is going out. So this variation is called the impedance variation, because blood is conductor in nature, and whenever some amount of blood is coming through the artery and going back through the vein, the amount of the conductivity or the amplitude of the conductivity of this material part or this body parts will be changing. So impedance variation will be found as the time varying signal, which will be correlated with the ECG, because blood is only flowing with the pump of heart, and heart is pumping with the help of the ECG generated or ECG signal generated by the sinoatrial node. So that type of impedance variation could become correlated with the ECG, and we can get several type of parameters called hemodynamic parameters to be calculated with the help of formula, either say stroke volume or cardiac output proposed by the several researchers. So that type of things are useful, and some devices are also commercially available for measuring the cardiac output with the help of say non-invasive technique like impedance cardiography. Impedance spectroscopy is obtained is found very popular for the material science, as I discussed in the say material characterization like photovoltaic cells and battery analysis, and civil structure analysis in the mechanical structure analysis. So in many fields the impedance spectroscopy is found. Recently, the carbon fiber reinforced composite known as the CFRP, that material which is very popular for its high strength to weight ratio, and which is replacing aluminum in the aeroplane construction. So that type of composite materials can be monitored either offline or online for damage detection or for detecting any kind of crack inside it with the help of electrical impedance techniques like electrical impedance spectroscopy. So body composition analysis is found by BIA, and there are some known formula and the information by which the BIA can be conducted. And this is the application of the impedance plethysmography, where you can detect the deep vein thrombosis. Deep vein thrombosis can be created whenever the blood is clotted inside the vein and it blocks the return of the blood to the heart. So blood will be coming from the heart, but it will not be able to return to its origin, means heart. So that's why blood will be accumulated with time and it will be making the leg swelled and reddish, and that will be very life-threatening disease if it is not properly detected. So which can be detected by the help of the impedance plethysmography. And impedance cardiography I have explained, where the several formula can be applied for calculating the cardiac output and stroke volumes, which are very important for detecting the health of the heart. So equivalent circuit parameter we understood. Summary: the electrical impedance is measured and that measurement is conducted or repeated for several frequencies. Nyquist plot is obtained. After the obtaining the Nyquist plot, that will be analyzed and we will get the circuit parameters. What equipments are required? Current injector, voltage measurement device, and frequency changing circuit. And then we will be able to get the tissue information or some diseases. So we have seen that some tissues which are seen in this microscope, tissues are getting swelled and sometimes tissues are getting damaged. So there will be some space which will change the impedance property of that. So disease can be detected like cancer also, skin cancers are also detected with the impedance studies, and many type of cancers like say brain tumors, breast tumor can be also studied with the help of impedance studies. Not only in the disease or health or medicine, but also in the food technology, the quality of the food can be detected by the impedance measurement. Juice quality detection, fruit quality detection, fruit ripening detection, all are possible to be conducted by the help of electrical impedance measurement. Even for the measurement of impedance of a concrete structure like a inhomogeneous material are also possible to be detected. Whether any iron bars are getting corroded underground, that type of techniques means that type of phenomena can be also visualized or can be monitored with the help of impedance measurement. So few experimental images are shown here where the fruits are detected, whether they are having some sufficient amount of water or not. And we have seen that the impedance of the cucumber, potato, all are different from species to species. And also if we measure the impedance for same material for time by time, we have seen that impedance is gradually increasing with the increase in the water evaporation from the natural drying. So here we can see that the impedance is gradually increasing with the time from day 1 to day 4 and 7 and 10 and 13 and 16. And after that, at the end of 2 weeks, we have seen that the impedance of the 13 day and 16 day are almost matching, means it is getting closer. That means the rate of the evaporation of the water is reduced due to the lack of water inside it after drying of 2 weeks. So that type of things can be obtained to get the freshness of the fruits. And also if we burn some tissue, then also, or if we boil some tissue, the impedance change will be also found drastic in amplitude, and where you can see that the destruction of the cell membrane will reduce drastically the impedance value. After that, some software are required because impedance analyzer will give some only the say tissue impedance curves, but for tissue impedance curves are not readily giving the impedance parameters. So that curves are required to be analyzed, and for the analysis, software-based the data fitting program can be developed. So one program is developed with the LabVIEW, where the data will be taken from the impedance analyzer or impedance measurement device, and that is not looking as the path of the circular arc. It is looking like a elliptical path. So from there, it is very difficult to calculate. So the program is written with the theory of the circle fit, and whenever this data is fitted, we will see that the earlier data, which was looking like a elliptical shape, the data is fitted in a exactly circular path. So whenever the circular path is found, then we will be able to get the equivalent circuit. So that will be the reactance obtained at the critical frequency, and this will be the amount of the impedance or resistance connected in series, and then this will be the total resistance. So that type of parameters will be obtained, either series resistance, parallel resistance, and the parallel capacitance. So what we did, we took the real component from the electronic circuit lab, like capacitor and resistor, so 2K and 1 microfarad, put in the breadboard, conducted the EIS, and then we got the data and we fitted the data and we extracted the data from this data fitting software, and we compared the value whatever is obtained from this experiment. So it is matching with the register, and there is some deviation in case of the capacitor. So that is around 5%, but it is required to note that the value whatever we have taken, that was ceramic capacitor, and that was having tolerance around 10%. So means the 0.1 microfarad will have some larger value and lesser value also. So that was not the accurate one itself whenever it is manufactured. So no resistor capacitor are found with 100% accuracy. So always tolerance are there, and the capacitor whatever was used, 104 capacitance, that is 0.1 microfarad, that was also having some errors. So it was not itself 1 microfarad, that I want to emphasize, and that's why a little bit more error is coming, but the register was 1% register, so metal film register. So that's why we got that type of accuracy. Definitely, if we have get the actual value of the capacitance, that definitely this error will be reduced. So we conducted a similar thing for vegetables, for carrot, cucumber, bottle gourd and all, and we fitted all this. And this was the studies conducted from our laboratory, and from the international research is also going on for studying the fruits. So like apple, avocado, then the nectarians, then the persimmon fruit. So many fruits or the food materials are studied, kiwi fruits and all. So here we can see that some chemical additives are found inside the liquid. So many foods are say coming in the news that some additives are there. So chemical identification in microscopic scale also it is possible if we have a say microfluidic techniques, and if we have the sample, fluid sample, either the juice or the preservative mixed some liquid food or any other beverage, then we can put in the say channel, microfluidic channel, and we can conduct the say impedance spectroscopy, and we can get the variation in the impedance. So fish quality is also studied, milk quality is also studied, and the ham meat quality can be detected with the needle electrodes. It will be minimally invasive, so little bit it will be inserted inside. If we put the electrodes on the surface, the sensitivity will be little less. But in case of the food, we can insert the needle, that is not a problem. But in case of human being or disease detection, the surface electrodes are always preferred. Cancer detection based on the electrical impedance spectroscopy, a clinical study. So the cancer is also studied because cancerous cell will be the uncontrolled growth of the cells, and that cell physiology is entirely different from the normal cell, and that could be visualized by the impedance property, because the cancer cell impedance will be different from the healthy cell, normal cell. And I will go to the microscopic analysis very quickly. So I am just keeping that. These are the case studies and the example in which the impedance spectroscopy is found for detection of the cancer or the breast cancer. And now whenever the biopsy is done, the breast cancer tissue or any cancerous tissue or tumor can be taken for the laboratory explanation, and with the help of microelectrodes, one small sample of the tissue is also used for detection of the impedance, and that impedance will be also compared with the healthy tissue impedance, and which will give us the clear difference about the cancerous tissue and the health. So that is called impedance based biopsy. So that work is going on, and that work is under research also. So electrical impedance spectroscopy in the urinary bladder detection. So an impedance spectroscopy is there. Another topic is there, electrical impedance say tomography, and that is the imaging technique. So if I have time, then I will explain that. So impedance tomography is one kind of computer tomography by which the imaging can be cross-section image of any domain can be visualized with the help of impedance measurement. So the urinary bladder studies can be conducted with the help of EIS, also electrical impedance tomography or EIT. Okay, so EIS with microsystems technology. So till that point, all the EIS measurement was found for the macroscopic measurement. So microscopic technology EIS is also very helpful. So in many cases, the microelectrodes are required, and microelectrodes can be developed either thin film technology or with the help of, say, 3D printing or any other means. So in the microscopic scale, very precise electrode fabrication is required, which can be developed with the help of 3D printing or the thin film development. So as we know, the 3D printing is a very precise technique by which the 3D models are developed with the help of any CAD model of the target object, and a printer with certain type of inks, either metal or glass or epoxy, any material are possible. So these are the possible materials can be used, either even the polymers, and some materials are also found as the filament, and that filament is heated to make it melted, and with the nozzle that is uh, given on the the material base from which the material production is started. So different kind of material technique, 3D material development technique, and where the fuse deposition modeling is also one major type of 3D printing, where the nozzles will be having either single or double or many, and the different color of filaments can be taken, and so that you can get different type of the material with some target color also. And this is one example of microscopic electrode used for the say impedance measurement technique, and that impedance measurement techniques are having some oils with microelectrodes, and that electrodes will have the 4 electrodes, and that 4 electrodes, outer 2 electrodes will be for current injection, and inner 2 electrodes will be measurement of the impedance of the material, measurement of the voltage. So utilizing the current data and voltage data, we will be getting the impedance of this well, that well, and so 4 sample can be studied together. Then other microscopic, other microelectrode development of the 3D printing devices. So EIS will be studied here, and some microfluidic devices are also possible to be developed with the help of some MEMS technology, and where the impedance measurement of the body tissue will reveal several type of biological problems. So microfluidics, natural microfluidics are found in the lungs, where the air and the air means the carbon dioxide and the say oxygen are transferred or exchanged for purifying the blood. So these are the microfluidic vessels, the tiny blood vessels which are surrounding the alveoli in the lungs. And you can see by this animation that the oxygen is entering to the blood vessels, and it is added to the RBC, that's red blood cell, and the carbon dioxide is exerted, and that is the alveoli, and this carbon dioxide will be coming into the alveoli, and that carbon dioxide will be sent out from the body. So oxygen is coming to the blood and carbon dioxide is going. So this type of microfluidic experiment can be conducted and studied in the simulation model. So with the help of the MEMS technology, we can develop that type of microchannels, and you can put some blood samples, and you can study the carbon dioxide extraction and the oxygen addition. So these are dimension of the red blood cell, so that we can understand that at what dimension it is there. So accordingly we can micromachine our device like a microfluidic channel. Otherwise it will be either very larger than the blood flow, or it will be very narrower for the blood particles. So example of one microfluidic device where you can apply the biotechnology and we can study the cell culture or any fluid analysis, body fluid analysis. So with the help of microsystems, we can go for the lab on chip or organ on chip, which are also the very emerging field by which one lot of experimental chemical analysis can be done in a microscopic scale. So many advantages are there for the microfluidic flow, and for the organ on chip, one of the major advantages is that it will reduce the animal experimentation, and also for drug analysis, drug delivery analysis, or the reaction of the tissue with the incorporation of any drug or the application of any new drug, that can be studied in the organ on chip, which is very, very important for developing any kind of, say, drug or any kind of vaccines. So with the help of microtechnology, we can go for the several experimentation in biotechnology, biomedical and clinical analysis. So wet lab, wet experimentation, or the macroscopic experimentation with lot of sample volume are avoided. So in case of microfluidic, a very teeny amount of sample is required for analysis. And in many cases, the amount of sample is not available. So in that situation, the microfluidic devices are very, very important. So these are the some other parameters which can be studied for the microfluidics. So I'm just skipping that. So these are the case studies where the microfluidics are say studied with the help of impedance spectroscopy. So monitoring the cell level studies also is possible for the help of microfluidics using the EIS. So microelectrical impedance spectroscopy. So that is called sometimes microelectrical impedance spectroscopy, because the impedance spectroscopy or electrical impedance spectroscopy is utilized in the micro scale. So microfluidic device for impedance spectroscopy analysis of biological samples. And even using the impedance spectroscopy, so we can say the single cell analysis. So multi-channel electrical impedance spectroscopy analyzes the microfluidic sensors. Utilizing the microscopic sensors, we can study the flow of single cell. Whenever the cell is allowed to flow through a microfluidic device, we can measure the impedance, and if the cell line is with a single cell, then we will be able to get the impedance of single cell. And with the help of some animation, we can also, these are the model of the organ on chip. So several organs can be mimicked and developed in a particular chip, and we can get this material, nano and micro materials, which is used for developing the microfluidic chip. We will give some channels so that the fluid can flow, and with the help of the electrical impedance spectroscopy, where the impedance measurement will be conducted across this fluid flow. So micro electrodes will be connected here, and another instrument will be incorporated in the, say, organ on chip or laboratory on chip, and then the fluid flow will be analyzed by the impedance also. So this type of entire laboratory will be implemented in a particular lab on chip, and the microfluidic analysis will be conducted, and parallelly the impedance studies will be conducted with the help of microelectrodes. So lung on chip is also developed, kidney on chip also developed, heart on chip also developed. So these are the references I have given. So this is from a book published by the Elsevier. And blood-brain barrier, which is very important physiology for one kind of disease detection or medicine analysis, means we will have the one extra protection in the vessels in the brain, so that the harmful materials, the harmful microbes or the other materials which is not good for the brain is not allowed to pass. So in case of normal blood vessel, there will be some pores through which the material can go in or go out. But in case of the blood vessel, whatever is there in the brain, there will be some extra protection, and this protection also is visible around the blood vessel, and also we see that the pores are not open. So this will be very selective for allowing some material to get into the brain, and also some other protection is there. So the material which is there inside the blood, it has to cross two barriers. One is the vessel pore, which is closed. Another one is this extra material. So that type of protection is called blood-brain barrier, and that is also very important for giving any medicine to the brain. So if we put any medicine in the blood, so it will be carried to the brain, but it will not be allowed to get into the brain tissue by this protection. So the selective opening should be there. So that type of blood-brain barrier is very important physiology of human anatomy, and we can study that in the micro scale, and that is very emerging field. And electrical impedance based analysis of this blood-brain barrier developed in the microfluidic range, and that can reveal several information which is very difficult to study in the real animal studies. And also if we go for the animal studies, the sacrificing of animal life is also be there. So avoiding that, we can conduct the blood-brain barrier based on the microfluidic technology, and we can study it with the help of electrical impedance spectroscopy. So there are some other examples by which we can study that. So we will skip that and we will go to the some nanoparticle based analysis. So we will skip that because a lot of studies are conducted on the organ on chip. So I will go to that and we will see how the single cell flow is changing the electrical current lines whenever it is passing through a microfluidic channel. And we are getting the signal here from this amplifier, and we will be able to analyze the cell property with this microfluidic device. Some commercial instruments are also available for impedance based analysis for this microfluidic devices. So I have given the website name from where I have collected that. So utilizing the MEMS and nanotechnology, we are able to develop the channels through which the sample will flow, and there will be some other instruments for studying the electrical impedance. So there are some other companies by which you can also buy some ready instruments by which you can study the microfluidics and impedance based analysis of cells in the microscale or in nanoscale. Now I will come to the nanoparticles in tissue engineering at the last part. We have seen that the nanoparticles are very advantageous for enhancing the electrical conductivity. If the gold nanoparticles are used, so electrical conductivity is enhanced. In some cases where the electrical conductivity is not much in some materials, that can be enhanced with the help of the nanoparticles. And also some nanoparticles are also used for injecting some medicine, for destroying some unwanted tissues like cancerous cells. So nanoparticle technology is an emerging field by which we can do several diagnosis as well as therapies. So in case of electrical impedance based techniques, we have seen that nanoparticles are useful for increasing the sensitivity of the materials. If the sensitivity is found less, then we can apply some nanoparticle technology and we can get so effect of gold nanoparticles on the electrical impedance of the tissue on low frequency ranges. So if the frequency is less, then we will find some impedance will be more. But if we inject some gold nanoparticle, the impedance of the material will be injected. And sometimes the information at low frequency is also required to be studied. And especially apart from the biology, if we go for the material like carbon fiber reinforced composites, say any other material which has the very high resistive material like epoxy and all. But still, if we want to apply the electrical impedance, because the electrical impedance based techniques are fast, low cost and portable, so that methods is very useful for several technologies, like several field of engineering, like say mechanical engineering, civil engineering and aerospace engineering. So this type of techniques are very useful for identifying any damage and cracks inside the civil structure or mechanical structure or aerospace structure. But still, due to the material property of the epoxy, there will be less impedance. So if we inject some material or mix some nanoparticles, say any metal particles, metal nanoparticles or metal composite nanoparticles, then it will be enhancing the conductivity of the material and the electrical impedance based. So after adding the nanoparticle, definitely we have to check whether the strength property or any other mechanical property has been altered or not, or if the alteration is under the limit or expectation or not, that should be always done, and then we have to go for the impedance spectroscopy. So wherever the impedance spectroscopy is not suitable for getting the enough sensitivity, the nanoparticles are applied in this domain. So the major domain is civil, mechanical, and aerospace. But in case of biomedical field also, a lot of examples are there. So few case studies are done. So nanoparticle enhanced electrical impedance. So we can see that nanoparticle enhanced electrical. So the nanoparticles are used for enhancing the electrical impedance and its potential significance in image tomography. As I told, there will be another technique which is called electrical impedance tomography. So that is giving the cross-sectional image, and it is called electrical impedance tomography. So that is a quite a new technique, but that technique is applied for several disease detection like breast cancer analysis, brain tumor detection, and the transthoracic imaging. So that type of imaging will give us the anatomical visualization as well as the information about the tissue property in terms of electrical impedance. So, but in case of electrical impedance, if we use the particular targeted material for enhancing the electrical impedance sensitivity, then the material or the system will have more accuracy, and especially the EIT will have the by the virtue of the ILFOS technique, the electrical impedance will be having more errors. Electrical impedance tomography will have more errors at the output if it is there inside the input. Okay, so I will come at the last part, that is the nanoparticle. Yes, that is also one kind of electrical impedance tomography where the gold nanoparticles or carbon nanotube electrodes are used for the frequency stable microelectrical impedance tomography. So in some time, the electrical impedance tomography is.
Sir,
Yes.
sorry to interrupt you,
Yeah, please.
but sir, it is my kind request that our next
Okay.
speaker is in wait.
Okay.
Okay.
Okay. Okay. Okay. So
Uh,
I'm just closing that. Okay.
Yeah, please, sir. So we will have another talk because
Okay.
you have given a very nice talk,
Okay.
interesting talk, and this is
Mm-hmm.
the very much related to the human body.
Mm-hmm.
So we will have another talk in any other conference or workshop. Okay,
Okay.
sure.
Okay. Okay. Okay.
Okay. Thank you.
Okay. Yes. Yes. So as I told that in nanotube or epoxy nanocomposite based piezoresistive strain sensor also can be developed. So it is for uniaxial cyclic static tensile loading detection. So that type of material identification or the material property identification can be conducted with the help of nanoparticles associated with the EIS technique. In the cementitious material or civil materials also, the nanoparticle based the electrical impedance techniques can be obtained with some more sensitivity. So as a summary, I will just conclude my talk. EIS is a material characterization technique. EIT is fast and portable tomography technique.
All the sample था
Yes, yes,
एक
EIS
मेरा skip
has many
leg
applications
रहा है
for
ना.
non-destructive evaluation,
उसके बाद
and
में
EIT can be used for imaging the material cross-section of the evaluation. The impedance properties can be enhanced by adding the nanoparticles or the nanomaterials to improve the sensitivity of the EIS and EIT based scanning. So EIS and EIT can be applied characterizing the microfluidic chip, organ chip, and the civil material and the mechanical and the aerospace material for improving the sensitivity and design. So I thank my research supervisors and collaborators with whom I have worked and learned a lot of things. And I thank my institute for giving me the platform for continuing my research. I thank Dr. Rajendra Kumar Tuchania for giving me the opportunity to talk about the research on the EIS and EIT with the help of nanoparticles and enhancement of the sensitivity. I thank the Department of Metallurgical and Material Science Engineering, UNIT Jaipur, and all the faculty members of the FDP, and I thank all the participants who have spent their valuable time for listening my talk. Thank you very much.
Okay, thank you, sir.
Thank you. Thank you
Uh,
very much.
Bera sir,
thank you,
very
Tushar.
nice
Very
lecture.
thanks, and a very nice talk, and it is related to our human body, which materials we require, and fluid also, है ना? So it is
Thank you.
very nice talk and informative talk to our participants as well as us. And from participant side, anybody some query from participant side? Sir?
Hello.
I think Tushar, nobody want to ask any question.
Okay. Okay.
They are in wait to another our speaker.
Okay.
So
Okay. No
very,
problem.
very
Thank you
thanks,
very much.
Tushar.
Yes. Yes. Yes.
We
Thank
will
you.
be
Thank
touching
you.
for the next collaboration.
Okay.
Very
Okay.
nice.
Thank you. Thank you very much.
Participants, please you click on the link we send you on WhatsApp as well as your mail for the next talk. This talk will be ended here. And for next talk, you will be click on the our which is link I send you WhatsApp as well as mail.